Okay, so today we're happy to have Jens Hoppe, who is visiting us for about a month. He will be telling us about some progress in membrane theory.
Yeah. Slightly less enthusiastic than I'm usually. I got some problem with my sinus. I don't know, aeroplane, apartment is very cold. And I'm taking antibiotics now, so I'm a little, I don't know. But it will, while I talk, I think I will be refreshed, hopefully you too a little bit. So Dirac wrote the first paper on membranes like 60 years ago. He wanted to explain the muon as an excited state of the electron. I will start a little bit with classical solution because it shows how difficult the topic is. So everyone, first one Dirac, but everyone who worked on it finds it's a spherical symmetric solution. So you just assume a sphere and it's depending on time and you get a pulsating sphere and the radius is some elliptic function. So that's simple. But apart from that, in 4 dimensions, if you want a membrane, so a 2-dimensional closed surface moving in R3 such that the world volume swept out in 4-dimensional Minkowski space is minimal or extremal, zero mean curvature. For 30 years, that was the only solution, the spherically symmetric. Then by chance, I found one which looks like this, t squared plus x squared plus y squared minus z squared times t plus z squared equal to c. Now in Minkowski space, there are always space-like and time-like manifolds or light-like. And membrane theory, the physical one, so that the particles or the points on the surface move with velocity smaller than 1, that would be the case when this constant is smaller than 0. So if you take the set of points t, x, y, z in R4 or in R31, satisfying this equation, you get something which is a membrane solution. So every t, but that's infinitely extended. And that's like 30 years ago. And then again, big gap for decades, no new solutions.
Sorry, so what's special about that? It can take any equation.
No, you want it to be a membrane solution, it has to satisfy an equation.
So this satisfies the equation of motion.
Yes. Yeah. And so here I write it as a level set, and then you get an equation, interesting equation actually. Eta mu nu, eta rho lambda minus eta mu rho, eta nu lambda, mu. I write it, everything costs time, but I write it down because this is not so much studied in physics. So u is a function of x mu, and the condition that it has zero mean curvature or it's an extremal manifold is this equation, where index means differentiation. U mu is du by dx mu. These are second derivatives. And that's one way to find solutions. Actually, I didn't find it this way because you have to make an ansatz. It's always so easy to verify that something is a solution. But now the interesting thing about this equation is that if you have a solution, every function of u is also a solution. That's not what we usually are used to, but that has to do with it. It's called geometric equation in mathematics.
Would you say what u is?
U is, for instance, this minus c or without this c. So the left-hand side would be u of x. So it satisfies this equation. So if you want to find membrane solutions as level sets, you have to solve this equation. And the interesting part, and actually the second reason why I mentioned it is interestingly Dirac, when he gave the membrane electric charge and so on, he mentioned this, or that was his approach. Okay, I have to hurry to come to the things which are hopefully more interesting or closer to the things. Also, I tend to forget, and it's just so much that I maybe want to mention and use the time of visiting here. There's one thing I don't want to discuss in this lecture or talk, but it would be good. I want to mention it, and this is the following statement. I found it like 4.5 years ago, wrote 3 or 4 little papers about it. Any bosonic system, maybe finite dimensional, which is supersymmetrizable, meaning that you can consider an extension of the bosonic theory, which then gives you a supersymmetric Hamiltonian. Any such system has a Lux pair. So you can write, if you write down the classical equations of motion, you can write it in the form L dot commutator of L with M. Now this comments on one very important aspect of this BFSS model or membrane theory or whatever. And that's the puzzle about integrability and chaos. So where there was a question.
What is L?
Well, Lux considered in the context of, what was it, KdV equation. For the first time, by the way, he died 4 days ago, age 99. Remarkable person. So L is an operator. So whenever you can write down the equations of motion you want to solve in such a form, where L is some object in the Lie algebra, M is an object in the Lie algebra, and the equations of motion can be written in this form. The nice thing about this is that the traces of the powers of L are time independent. So if you have a finite dimensional system, usually, and even better when they have spectral parameter, this is the road to integrability. Now, the weird thing is that again, with these matrix model or BFSS model, supersymmetric quantum mechanics systems, reduced Young-Mills, it's an exception. And it is just as strange as going from bosonic to supersymmetric. So, yeah, sorry, scattered results. If you start with this Hamiltonian, that's a baby example. That was my master's thesis, actually. So that you have this Hamiltonian. We were too stupid to determine, does this have a discrete spectrum? Does it bind or not? It's very simple one-line proof. And actually, but we didn't know enough mathematical physics. So bosonically, it binds, has a discrete spectrum, and independently Barry Simon, who was asked by Jacques, who had been told by Goldstone, answered this for the matrix models, for the bosonic matrix models in a beautiful way. He wrote a paper, 7 different ways of proving that all these matrix models, the bosonic ones, have purely discrete spectrum. Independently, Lüscher did the same thing, considering reduced Young-Mills theory. So the weird thing here is, or not weird, it's not weird, it's just subtle. This is a bosonic. Then you go to the supersymmetric system, and surprise, surprise, it's no longer discrete. The spectrum, we know, is continuous. And the important thing of BSSS was the interpretation of that it's good. I mean, I actually thought always that that there will be a nice explanation, but semi-autistic as I am, I didn't think so much about the physics. So Nikolai used to make fun of me when they proved the continuity of the spectrum. He said, Jens, why are you still working on membranes? It's dead. I mean, it's the end. And then I said, well, no. I mean, don't. It's so interesting, the structure of the model. I don't care. There will be an interpretation, and BFSS found it. Okay, so just as there is a thing like, which is somewhat unusual. So classically, the idea that when the motion can extend to infinity usually tells you there is a continuous part of the spectrum by a theorem or whatever. So it's a subtle problem. Then you go to supersymmetry, it again changes. And I have a feeling that the question of chaos and integrability in these models is just as subtle. So Lux pair, I'm claiming our matrix model equations. Aidan, yeah?
Sorry, I just want to understand for the bosonic versus supersymmetric, is the intuition that in the bosonic case, they're like classically it looks continuous? And then if I add in quantum mechanics.
If you're very naive and not trained in mathematical physics, you would say, oh, but I have motions where x of t or y of t is equal to 0. So I have classical solutions which extend to infinity.
Yeah.
Then maybe there should be maybe some discrete states and then higher up a continuum.
Yeah.
But this is not the case.
But then the statement is when I add in supersymmetry, that protects this. That protects these flat directions.
Yes.
Yeah, okay.
No.
There's a simple way to think about that. If you look at the potential here, so x equals 0 and you make y large, this is the flat direction. But the potential becomes steeper and steeper as you go up in y.
Yeah.
So the effective motion in the orthogonal direction, like a harmonic oscillator, you get a contribution from the 0-point energy of the harmonic oscillator. So the effective potential is something, the flat direction is lifted.
Yeah.
Because the perpendicular motion gives you a 0-point energy. However, in the supersymmetric theory, there's a fermionic contribution which exactly cancels that.
Yeah, okay.
The flat direction remains. Sorry.
No, you help. Thank you. And it maybe I just shut my brain and not make too many side remarks because I claimed I will do certain things in this talk and I should do at least some of them. And I think there is a very interesting question about the questions of chaotic motions. So even in the old days, Nikolaevsky and Schur, 1972 or so, they claimed this is a ergodic or purely chaotic system. And then 20 years later, Dahlquist found a periodic solution for this case, but with a long period, again, very atypical. So, yeah, so, and I don't know, Hanada, Schenker, people wrote about chaos in this matrix model. I say, well, there is a Lux pair. Now, the way out, or the unfortunate thing is that, yes, there is a Lux pair for all these supersymmetrizable systems, but it's always in some way trivial. It doesn't give you any other conserved quantity other than the energy. So, but still, it's so peculiar that the signal of an integrable system are Lux pairs, or one of the few signals. So now I go back to classical solutions. So that was 30 years ago. And then recently I found several explicit classes of classic solution. The mathematicians are very interested in this, like Hüsken. And it's remarkable, they are also polynomial, like for instance, t squared minus x squared minus y squared plus z squared is x t plus z power 6, only one power works, times a constant, but in this case, it has to be bigger 0 to be membrane theory. And again, infinitely extended, but the one I want to start now. Now, the talk now starts, part 1 of the 4 parts, is the following solution. T squared plus x squared plus y squared minus z squared plus 3c squared t plus z 4 minus 6c plus z squared square root of x squared plus y squared equals 0 and c smaller than 0. Now that is, I called it the and I've given a non-commutative version of that, which gives an exact solution of our matrix to slowly come to physics or so out of this classical solution, there will come out a non-computative version of this minimal or membrane solution, which will give an exact solution of that. Now, this I've found again in some other way. And it's like, I forgot this way or this way. Aidan kindly, I never plotted, or I don't know how to do that. And I asked him, and he made a movie out of this. So when you pick seed like -1, and then you view it as a motion for every t, you plot how the surface looks, and it's a droplet which moves in one direction, and it has a sharp singularity. And one of the points on it moves with velocity of light, so that's where the metric is 0. So there are two kinds of singularities. Okay, now in what way does it give to the solution? Well, I have the light power. The simplest, this is axially symmetric. And the last topic, that's the one closest to my heart maybe, is the integrability of axially symmetric membranes in 4 space-time dimensions. Because I think the only chance, or a good chance, to make progress with the problem is to understand classically. I mean, if you prove that you have a way of generating infinitely many solutions, it will help you for the quantum theory. On the other hand, or the non-commutative theory. On the other hand, we should not forget, the matrix theory is more clever than the classical theory. So when you start with classical membranes, Olsen and I found this fuzzy sphere approximation. We derived the matrix model, and we did that for the sphere. Then people noticed that this can be done for the torus. I was one of them. And then some friends and me, and we conjectured that it can be done for any compact two-dimensional Riemann surface. So there's a theorem. One more remark. Yeah. So you take a two-dimensional compact surface with the density. So basically, you have a genus 0, 1, 2, and so on. And then there exists a map from functions. So alpha goes on to infinity. And then there exist numbers n alpha, which grow when alpha grows. And there exist real numbers h alpha, which decrease when alpha goes 1, 2, n. And the map is, so there exist maps T alpha, which map functions on the two-dimensional surface to matrices of size n alpha by n alpha. If the functions are real, the matrices will be Hermitian with these 4 properties. The most, one is that the norm stays finite. One is that products converge to product, T alpha of F times T alpha of G converges to T alpha of F times G. And then the one most important maybe is this commutator one. So the commutator of the matrices converges to the image of the Poisson bracket, where the Poisson bracket is defined with this rho. So the Poisson bracket of F with G, it's 1 over rho, epsilon Rs, ERF, ESG. F and G are functions on this two-dimensional surface. These are derivatives with respect to the local coordinates. This is a flat epsilon tensor. This rho is important. And because of this would go to 0, so you have to divide by something else which goes to 0, and that's this H alpha. And this goes to 0, and then the last point is that 2 pi H bar times the trace of the matrix converges to the integral of the function. Now, the reason I quickly mentioned this is, so for the sphere, this was done in 82 by Goldstone and me, I mean, or for some way for the sphere. The torus was about 10 years later, Fairley, Fletcher, Sachhaus, and I myself. And then we conjectured it's for higher genus surfaces. You can prove it. The proof is by Bordemann, Reinken, Schlichenmeier in communication mathematics physics. But up to now, there is no example of this for higher genus surfaces. We know how this map looks for spheres and tori, but we don't know how it looks for G equals 2 and so on. Very nice thesis, nice problem to work on. Okay, now, why did I mention this? The key was I said matrices are more clever. So if you start with classical membrane theory, you have to say which topology. So you have a two-dimensional surface which moves and sweeps out some manifold in Minkowski space. You have to discuss separately spheres, tori, and other objects. You find this matrix approximation, and for these compact surfaces, the statement is that the correspondence is between large n limits of finite matrices to the classical continuous case. Now, there was a puzzle. How can this be? Why? And we still don't know how actually this limit looks like. So if you take the BFSS model, what exactly do you do with n goes to infinity to, in the end, get a spherical membrane or a toroidal membrane or some star product membrane, more complicated objects? The matrix theory contains everything, all the topologies. That's why, sorry, this 3 minutes wasted was, or unplanned, was because of this matrices are more clever. And there's yet one more thing, which I will not have time to discuss in detail, but there's a host of classical string solutions which have not been discussed at all by people. They are wonderful solutions, like for instance, t squared is x squared plus sinh squared y. So the set of points in R3 or R21 satisfying this equation. For t equals 0, it's a point, and then it grows, and it grows forever. It's a zero mean curvature surface. It's a classical string solution. Even no singularity. But when you try to find the solution with matrices corresponding to that, that's my latest thing, which is not published yet. I'm working with this with Giovanni Felder. It seems that the matrix version does not exist. And the reason is that these are infinite energy solutions. So the fact that it grows and grows and grows and grows means it has infinite energy. And okay, I come back a little bit to this point. Now, the solutions are in this paper that I mentioned in the abstract, which use two copies of SO12 representations. So you can construct a solution of this for D equals 2, which would correspond to 4-dimensional, because these are light cone version. And then you have to also satisfy I and I dot. So if anyone is interested in an explicit, so nice, very interesting class of solutions, it it has more than one parameter. I wrote in the abstract one parameter, but it's given in terms of representations of the so-called fuzzy torus. So you have a like H1 with Y is IH2, H2 with Y with minus IH1 and H1 and H2 commute, and H1 squared plus H2 squared is 1. And any representation of this leads to a one parameter, and there are many representations of this, to solutions of that. Now, to come to the other topics, already 25 minutes is gone. So I don't go explicit. The preprint number is 2302. No, not here. 02. 1316. Okay, now the second thing, which was in the abstract, was this recent work. So if you have equations like that, you could consider them as static solutions of that. And that's what Kornalba and Washington Taylor did. I forgot when, 10, 15 years ago. Kornalba was getting his PhD here in Princeton, and they considered solutions of this where x1 plus ix2, let's say, is w, and x3 plus ix4 is w squared, and w is a kind of x on some Fock space, little wn times n plus 1. And then you plug this into these equations, where d would be 4 in this case. And then you get an equation for the modulus square of wn. And I just want to make a quick comment because I mentioned it in the abstract. So you get the following equation: Vn times 1 plus Vn plus 1 plus Vn minus 1 equal to epsilon times n plus 1. Epsilon, some small parameter. And you have to solve this. Now, because Vn, you can easily solve it. Vn plus 1 is given by this equation. But you want all Vn's to be positive. So in order to get a solution of this form, you have to pick the V0. So you pick V minus 1 with 0. And you have to pick the V0 such that all the higher Vn's are positive. Now, Kornalba and Washington Taylor noticed, I think it's called holomorphic curves for matrix theory or so. They noticed that this is an interesting problem, and they said it's probably unique, the V0. They had some numerical studies on it, but that was it. Then in 2019, I worked with Arnlind and Kontsevich. I spent a year at IHS, and we took up this among other solutions of this. And I found tons of things about this, but still we couldn't really solve it. And then recently, within the last month, we know now the explicit, there is one V0, you can prove it, and it's an interesting solution. And it's related to orthogonal polynomials with complex densities. So there is a measure. So you have functions of complex variables. And the measure is something like this, e of minus z bar. And the measure is e to the minus a z epsilon delta z squared plus I over 3 z q plus z bar q dx dy. Now for polynomials, this does converge in contrast to things when there was no I here, which had been considered in the context of Laplacian growth problems. Diekmann, Zabrodi worked on that. And Giovanni Felder, with his student had some time ago, worked on that too without the I. And they got recursion relations. I noticed that they got recursion relations which were pretty similar to that. So when I was in Zurich, I went to Giovanni and asked, can you please, because I'm not so good in these formal things, and he basically the paper we wrote, it's in the abstract quoted, it's mostly his work. He could answer all it, and this is the answer. So there is this theory of orthogonal polynomials with this complex density is related to this, and it answers what the V0 to take is. So the V0 you should take is half and it's 1/6s minus k prime of 1/6. K is Bessel function. And S is 1/6 epsilon. Where epsilon goes to 0 is S goes to infinity. -1. So there is one unique for every epsilon. There is one choice of V0, which will make all the Vn's positive. And it's nice. This is a discrete Pauli equation. And I wrote a little paper on that, and there was also a paper by Clarkson on the web later than mine, but they started much earlier, so they should get a lot of credit for that. They have a very interesting explanation of this in terms of Pauli 5 equations, Backlund transformations, and they got also this. And Giovanni and I have a different view now on this. Okay, I better come to maybe more matrix models and membranes. So one can also give formulas for the Vn's. And the reason why I mentioned this is because I wrote a little paper called Quantum States from Minimal Surfaces. So these are quantum minimal surfaces. And the Vn's satisfy a Riccati equation. Minus 1/6s times n. And one way, so Clarkson and Ruhon, and they did huge machinery, complex geometry, Sakai classification of discrete Pauli equations, thick paper, 40, very nice. But they had a hard time again proving the positivity, and I found a very simple pedestrian proof. So if you know that they satisfy this equation, and you know from this, you know that the Vn goes, or epsilon goes to 0, like epsilon n plus 1. So if epsilon is positive, this is positive. And it's absolutely elementary if that it has to stay positive. Because if you have a function which is positive here, and if it wants to go, here's S, it reaches 0 somewhere, so then Bn is 0, but this is negative. But the derivative here is positive. So if the Vn satisfies this Riccati equation, it's a proof that the Vn's are positive. Now, yeah, excuse me.
Is there some physical meaning to the z cubed and z bar cubed in the measure?
Here,
Yeah. Why do you assume this?
well, we considered this for arbitrary powers, and you can also do this for but this particular equation has to do with power 3. And if you have arbitrary positive powers, it gets more complicated. The measure, you have to have automorphisms of some it's more complicated. You cannot simply take g of minus z, but we found a way to define this scalar product. And the reason why I wrote 3 here is because it gives this problem. And now, the reason to mention this, apart from that's maybe my most recent work, but that's not a reason to mention it, is it's related to Schrödinger problems. So any Riccati equation gives rise to a Schrödinger equation if you put Vn as some number phi n h over logarithmic derivative. So you get a second order linear equation for phi, and it looks like this: phi n double dash plus 2fn phi n dash minus 4n plus 1 over 6s phi n equals 0, and then you get rid of the linear, the first derivative, and then you get potentials, which are like this: minus the s squared minus 2 over 9s squared h1 1, which comes from v0 you get this, from v1 you get this one, and h2 is still simple, and then h3 becomes complicated. Now, the reason I mentioned that is there were ideas, just a speculation, that these kind of potential have to do with Riemann zeta function to prove that the zeros are as they are. And that's an interesting relation to these matrix model equations, I think. So if we think that this is fundamental and describing non-commutative space-time, that's a potentially interesting.
What S is? You started with some recursion relation.
Sorry?
Could you say what S is?
S is 1 over 6 epsilon.
Sorry.
Epsilon is the parameter in
Okay,
here,
okay, fine.
and so epsilon goes to 0 as S go to infinity. And yeah, they are of course scale invariant. So they are all zero energy solutions of these, but okay, losing time. Now, I'm coming closer to the heart of the matter and to the end of my talk, unfortunately. So we have also these equations. Of course, the supersymmetric case is the more interesting, but let's start with the bosonic ones. So here it's the solutions of these would be either considered time-independent solutions of that, or non-commutative minimal surfaces in Euclidean space. This would be non-commutative string theory solutions. And apart from some, actually, sorry, I don't know. He wrote a paper there. I don't know how to pronounce your first name. You had some solutions of this with G, X, and P or so, with banks, I think. But they are, I mean, there are infinitely many minimal surfaces, so we should get infinitely many solutions of these, and I think they can be found explicitly. I claim that one can, and I found a procedure in this paper with Kontsevich in 2019, or we found, and it has to do, so the simplest classical solution for strings is this one, P cosine P cosine phi, sine phi. It's a circle which shrinks. Round circle, shrinks, and it blows up again. That's a string solution. it's non-trivial to find the non-commutative version of this. So classically, these satisfy equations like this, where these are Poisson brackets. But you have to go to particular representation, parameters. The analogy between the classical equations and this, so there's a density here. It's always 1 over rho. And the equation, the string equations are this only when the Poisson bracket has a particular density, which is solution dependent. So you have to reparameterize this. Such that in the new parameter, x prime squared is 1. And then you can make out of this the solution of that. Okay, I come to the last topic. Sorry, I was too optimistic.
Wait, sorry, I just had a quick question on this.
Yeah, at the moment. So you write this now as you think of it as t tilde phi. And then the non-commutative version, the solution is simply this, where t and phi is IH bar. So there's a procedure how to get solutions of matrix equations when you know the classical. There was a question.
Sorry, are you claiming that you have found all, sorry, did you say before that you claim this gets all solutions to this?
Well, that's not in the paper yet. I claim that in principle, we should be able, because string theory we can solve, I mean, in a flat background and especially in 3 space-time dimensions, but in general, and well, not absolutely explicitly by writing down the operators, but semi-classical, yes. I mean, I have a direct correspondence. You give me a classical solution, I construct some solution of this, which at least when h bar goes to 0, satisfies that equation. Okay, I mean, the reparameterization here, no, everything costs time. But because I mentioned these solutions here, that's a very interesting topic. I hope maybe also next week or at lunch or next time we talk. These infinite energy solutions. So, yeah. I say it better in words rather. I like formulas more than words, but it's quicker. There is a statement. Any closed string moving in the plane, any initial condition will become singular in finite time. So you can start with any configuration you want. In finite time, you will have developed a singularity. It does not apply to the solution. So there's even a mathematical by Gangtian, famous differential geometer, and Nguyen, a mathematical theorem about it. Every minimal hypersurface in R21 of the topology of the cylinder has to have a singularity. There is no. But the way this escapes that problem is quite interesting. Because this doesn't in finite time. If you come from plus infinity, it reaches the singularity in infinite time. Okay, last topic, only 15 more minutes. That's the one maybe close. No, 2 more topics.
So isn't that one singular at t equal to 0?
Sorry? This is singular at t equals 0, yes. But it's the theorem of even the mathematicians is that string solutions in the plane, closed string solutions in the plane, develop a singularity in finite time.
T equal to 0 finite time.
Sorry?
Isn't t equal to 0 finite time?
Yes, but if you start from from, okay, you say at t plus infinity, you don't have a definite one. Okay, thank you. Maybe my mistake. If you start with any definite one, yeah, thank you. Maybe mistake of mine. Still, this is very special, but I get your point. If you take any finite time, any shapes, it is finite time to here. Okay. Now, the last thing. I will skip now this Lorentz invariance thing, unfortunately. So, please ask me in the question section. I want to comment. So, this fundamental structures of M-brane theory, that's of course quite important. Okay, maybe 2 minutes about it. So, we have this Hamiltonian over 2 eta integral p squared plus g over rho. And I take now not only membranes, but strings and higher dimension, whatever. Then there is this has in the light cone gauge only transverse coordinates. So you have xi from 1 to little d, which is big D minus 2. Big D is the space-time dimension. Then the x minus, which I call theta, is constructed from the transverse coordinates by solving some equations. Theta, dA zeta is p dA x, and theta squared zeta dot is a half squared plus g over rho squared. Now, when one discusses strings or membranes in the light cone gauge, one is happy that one of the coordinates drops out, the x minus. I say it's the most interesting of all in the game because you have to reconstruct zeta from these equations. And in particular, if you want the Lorentz generator, xi theta yeah, maybe like this. Yeah, something like that. And now, already classically, so you have a phase space, x and p coordinates, and you have to show classically that they Poisson commute. Now, the first calculation for strings of the critical dimension was by Goddard, Goldstone, Ravi, Thorne, where they quantized this Mi minus. They wrote it in terms of oscillators. They calculated this in the quantum case, and they got that only in 26 dimensions. It's 0.
But actually, it was Claude Lovelace.
Sorry?
It was Claude Lovelace who I think first obtained.
Thank you. So, who was the first?
Lovelace.
Lovelace.
Not in this context. Not in the.
Yeah, but he looked at the loop, one loop, and I think so.
I always thought GDRT was 9 You know, we can discuss later.
Well, it's not the history of science.
Anyway, so for higher dimensional extended object, this is even classically horribly complicated. And Goldstone in 1985, he sent me some notes. He proved this by a formidable calculation, inventing all kinds of methods. Quite funny, I have a copy here. I put it on when I gave a talk at CERN. I thought maybe it should be available. It's quite funny. I mean, first of all, the calculation is formidable, and it's not well quoted. The known papers are Marquardt, De Witt, Nicolai, they for the and Izawa, the Japanese people, and they don't. It's not obvious from their papers that the important steps were actually close. And now, when you expand this, so there is a zero in it. So there's a zero modes part. And then there is a part which has only non-zero modes. But there is a part which is linear into zero modes. This is quadratic, this has no zero modes. In the calculation with the oscillators, this is important to have this. And now, knowing that this is zero, you can conclude what this does. The internal part. And there is a surprise I want to write down before. If you calculate classically the bottom bracket of the transverse Lorentz generators, that's what I call dynamical symmetry. Well, for index reasons, you get, of course, Mij, the Lorentz generator, but you get the thing you want, the mass squared operator, or the classical mass squared. And this is very similar to the hydrogen atom. This is the Lenz-Runge vector. This is the Hamiltonian of the hydrogen atom. And there is the algebraic way of finding the spectrum of the hydrogen atom. Only this is much more complicated, this problem, because it's infinite degrees of freedom. I think there is a reasonable hope that one can calculate the spectrum of the extended objects algebraically. In relation to that. And the other thing is that the zetas satisfy, if you take the modes of the zetas, you expand in terms of some spherical harmonics. They satisfy an algebra which generalizes the Virasoro algebra. So the general consensus is that, of course, strings are special. The Virasoro algebra, which is central for the integrability of strings, cannot be generalized to higher dimensions. I'm saying no, there is, I called it reconstruction algebra. These structure constants, this is the Virasoro algebra for m equals 1, but it is there. Okay, 5 more minutes. So, I last 5 minutes. Axially symmetric membranes, classical in 4-dimensional Minkowski space. And I have 2 questions which maybe you can answer. I couldn't. Should make it a problem for, I don't know, Princeton qualifying or so. I'm sure some smart person will know the answer. So, if I discuss this and choose some clever gauges, all I have to solve are these 2 equations, R1 R prime plus Z dot Z prime. So apart from my sinusitis, which I hope will go away, I'm happy if I can solve this problem. So it's R dot squared plus Z dot squared plus R squared times R prime squared plus Z prime squared into 1. Now, they imply the second order equations for, so I'm looking for 2 functions of 2 variables, satisfying these 2 first order equations. If I can solve them, I have solved completely. I would know all axially symmetric membrane solutions.
Sir, the risk of being done, what did you write there? You have cosine theta and sine theta below it. Does it mean the
R multiplies both. This has 4 components.
yeah, that's what I thought, but I just wanted to.
Thank you. Thank you.
So you want to save yourself writing
Right.
for another line.
Yeah, and losing time by having to, yeah. Thank you for the still being
I
there.
was assuming that.
So you do the following now. You eliminate Z dot at Z prime. I mean, these are quadratic. And that the whole problem is this factor R squared. If R squared is not there, we have string theory, we know how to solve it. You will get the free wave equation, we know all solutions with some constraints and so on. Axially symmetric membranes has this non-linearity, it completely changes the game. I do the following. I eliminate Z dot and Z prime in favor of R, R dot, and R prime. So some complicated F, I will write it down in a minute. Z prime is then minus R dot R prime over F. And F is unfortunately pretty complicated. F squared is half 1 minus R dot squared minus R squared R prime squared. That's P plus minus square root of P squared minus R squared R dot squared R prime squared, which I call Q squared. So the expression for this F is pretty complicated. Square roots, very nonlinear. Now I say the dash of this has to be the dot of that. So I get an equation for R, only one equation for R. So I get some expression. And it looks like this. R double dot minus R squared R prime squared double dash. Sorry, I'm running out of memory now. I think like this. So question 1. I get a second order equation for R, and now comes the question for the qualifying or whatever. Is this equation Lagrangian or not? Find a Lagrange. You would think yes. Usually all second, I mean, the ones we deal, the problem comes from a Lagrangian. It should. I couldn't find, I tried really hard to find this. And the last thing, time is up. Is in this game, there are pairs of objects. So the free wave equation has solutions f of phi minus t plus t and phi minus t. Now that's the Lorentzian analog of Cauchy of holomorphicity or Cauchy-Riemann equations. Because of this R squared, we get, so the weird thing is that there is a partner. I don't have time to, this is V dot over R squared. So everywhere in this problem of axisymmetric membranes and 4 space-time dimension, there are partners which satisfying these kind of equations. That dot is V prime, that prime is V dot up to this factor 1 over R squared. So if this was not there, it would imply the wave equation. This way it implies that double dot is R squared, that prime. That's the way, I mean, that's the second order equation that follows from this. So that's the equation of motion. I don't know an interpretation. I would like to know a geometric interpretation of what V is. I mean, it's a simple problem. I know what R is. I know what Z is. I want an interpretation of what V is. And this whole problem, you write it in light cone coordinates. So the same thing. Then you get an equation, it's actually nicer. So here you get a real mess for little r, but in light cone coordinate, that's the simplest equation you can get for axially symmetric memory. You just need one function of tau, light cone time, and some other spatial variable mu satisfying this equation. The way I found this solution was by solving a corresponding solution of this. So, just like here we have R and Z, we have zeta. Zeta dot R squared plus R prime squared. And again, there is a partner of zeta. So this is kappa dot. And this is kappa prime over R squared or something like that. And I have no idea. And again, everything you write down. So, and tau and mu as functions of t and phi again satisfy these Cauchy-Riemann equations. I mean, these equations. And I don't, this must be a clue to how to solve this, but I don't know for the physical significance of this partner. So there is this kappa.
Well, I mean,
Okay.
if you dimensionally reduce on the angle, you have.
Sorry?
If you dimensionally reduce on the angle, you have a string with variable tension. I think that's just the T-dual.
So you think you understand what V is?
Yeah, it's kind of.
Oh, I'm very looking forward to that. That's why I mentioned it. Yeah, I mean, time is up, and sorry to probably not talk too much about things that you really want to hear, but the point was to mention several things, and then maybe during this day you can ask me if you're interested in some of the aspects, and I can tell you a little bit more. I mean, nothing is really close, maybe, but there are some qualitative points which I think are really important. This dynamical symmetry. I don't have a student now. I like calculations, but I need somebody to discuss. This is complicated. I mean, it would be, even for the string where one knows what comes out, it would be nice to follow this. It's mentioned in the abstract of the paper. That's 10, 15 years ago, fundamental structures of membrane theory. And yeah, I end my talk now.
Thank you. Questions?
I had a question about the minimal surface solutions to
Yes.
the static equation. So you said that they're solved by this recursion relation.
Sorry, there
You
is-
said that the solutions are parameterized by this recursion relation. The static solutions to this commutator equation
So
that give them.
the static solution of this, one particular static solution, was this one which I mentioned,
Uh,
this one.
Is this these recursion relations, can they also be seen as coming from a random matrix theory of some kind?
Right, that's that. So in the case when there is no I here, this is precisely the case. It comes from random normal matrices.
So there's, okay.
So that's an yeah, and because these random matrices, again, that's why I mentioned this Riemann hypothesis or whatever. So yes, there are, but we don't know exactly what the relation to random matrices is with this I. But there probably is a relation.
Without the I, what is the potential? In the random matrix theory?
Yes.
This is the potential.
Yeah, this-
I see, okay.
Okay, there are no further questions this time. That's okay.